With the drawbacks of Rayner's theory and valence bond theory, crystal field theory came up into existence. In order to account the limitations of valence bond theory and crystal field theory was developed by Bethe and Van Verecke in 1929. To understand the theory, it is essential to know how the d orbitals are shaped and especially how they are oriented in space. Out of the 5 d orbitals, dxy, dyz and dzx are called T2g, while dx square and y square and dz square are called Eg orbitals. The salient features of CFT are: the transition metal act as central cation. The ligands donate their lone pair of electrons to the vacant orbitals of this cation. The ligands are considered as point charges. Students, I request you to see the second point. Ligands are considered as point charges, which was proved wrong later in MOT. The bond between the cation and the ligand is considered as 100% ionic. It was Aditya, the previous day he called me and he was asking me how these cation and ligands are being attached. I told him to wait for it, and here in CFT you can see the third point saying the bond between cation and ligand is considered as 100% ionic, and it is also wrong proved later. The electrostatic force may be either ion-ion attraction or ion dipole attraction. The negatively charged electron cloud of ligands repels the valence electron of the cation. The crystal field is determined with the number of attacking ligands and the geometry of the metal ion. The relative energies of the d orbital will be different for different ligands. The magnetic character depends upon the extent of splitting of the d orbitals by a ligand. Greater the splitting of the d orbital, lesser will be the number of unpaired, and hence the lesser will be the magnetic character. I repeat this point once more. Student, be careful. The magnetic character depends upon the extent of splitting of the d orbitals by a ligand. Greater the splitting of the d orbital, lesser will be the number of unpaired electron, and hence lesser will be the magnetic character. And finally, to go, the shape of the transition metal complexes can be explained on the basis of crystal field stabilizing energy. Regarding the orientation of the d orbitals and the crystal field splitting of energy levels, here we can see in this case of a free central ion, all the given d orbital has the same energy and are said to be degenerate. On the approach of ligands, the orbital electrons will be repelled by a lone pair of ligands, and the energy of the orbital will increase. The energy of the orbitals lying in the direction of the ligand is raised to a larger extent than that of the orbitals lying in between the ligands. The conversion of 5 degenerate d orbitals of the metal ion into 2 sets of orbitals giving different energies is called the crystal field splitting. Hello students, here we are going with the crystal field splitting. As we have already covered the valence bond theory, Rayner's coordination theory, so today we are to go with a crystal field splitting theory. So in this theory, first you have to know about the d orbitals. You know very well the d orbitals, it looks like a double dumbbell. Now how they are occur? We have got the 3 axes x, y and z, and we have got 3 d orbitals known as dxy, dyz and dzx, and 2 more d orbital called as dx square, y square and dz square. Total we have 5 d orbitals. So these 5 d orbitals, how they are oriented in space, this is the first and foremost thing that you should know. When you go for the dxy, that means one of the dumbbell is facing towards x, is facing between x and y, is facing between x and y, between x and y. When you are going with the dyz, the dumbbells are in between z and y. While you go for dzx, z and x, you will have that between z and x you have those two dumbbells, so they lie between the axis. When you go for the dx square y square, that means it lies in the d and on the y, so they lie on the axis. And when you go for the z, dz square, so it will lie on the z itself. So these are the pictures that you have to learn while you go for the crystal field splitting. So when I talk about dxy, that means it is neither on the x nor in the y, but in between x and y. When I go for dyz, that means it is neither on y or z, it lies between y and z. And when you go for dxz, that means it is neither on x or z, it is lying between x and z. Remember, this x and z, they are 90 degree to each other, and while the y what we have drawn is also 90 degree with respect to x and z. So all the lines, all the axes are being drawn perpendicular to each other. So these are the structures or the shapes and how they are oriented in the space. This you have to know it. I would ask the students to see once more about the orientation of the d-orbitals in the space. Student, have a look nicely. Regarding the octahedral complexes, that is, the coordination number should be 6. The magnitude of splitting is denoted by a delta sign, and a suffix O is indicated for octahedral complex. Student, there is a relation, that is the splitting energy of the octahedral complex is equals to 10 dq. This you have to keep in your mind. The splitting energy equals to 10 dq, and the energy of the 2Tg is 0.4 of the splitting energy, which is less than the energy of the degenerate d orbitals. The energy of the Eg orbital is 0.6 of the splitting energy above the d orbital. The 6 ligands in the octahedral field, when being attacked by the metal ion along the 6 corners of the octahedron, dx square to y square and dz square, which are called the Eg orbital, lie along the corners of the octahedron. Student, I have underlined it, along the corners of the octahedron, and hence would experience greater repulsion from the attacking ligands, and are raised in energy higher than that of in the case of the other set of dxy, dyz and dzx. The result is that the set of 5d orbital is split into 2. Students, it happens that when you are being attacked by any such kind of fierce animal, you get extra energy. If you don't know how to climb a tree, you will see that you, in spite of not knowing how to climb, you start climbing the tree to save yourself from a growling animal. Similarly, Here when we have the metal with the d orbitals, the 5 d orbitals, say dxy, dyz, dzx, dx square y square and dz square, when they are being attacked by the ligands, by the electrons, by the lone pair of electrons of the ligands, they get excited. So when they get excited, they jump to the higher energy. They jump up with the higher energy. This is what we call as the barycenter. B-A-R-Y-C-E-N-T-R-E, barycenter. So when the d orbital electrons come to face the lone pair electrons of the ligands, they get excited and they jump up for a higher energy, and this is what we call as the barycenter. This set of electrons before was known as degenerate level, D-E-G-E-N-E-R-A-T-E, degenerate level. So the electrons of this level, when they were not being attacked by the ligand electrons, they are said to be in the degenerate level. But now when they are being attacked by the lone pair of electrons coming from the ligand to form a coordinate bond, they go at a higher energy. This is what we call as the barycenter. For the octahedral splitting, we will see that the dzx, dx square y square and dz square, they rise upward more and they split up. The dxy, dyz and dzx, they come down with a lower energy. So the 3 d orbitals comes with a lower energy called as dxy, dyz and dzx. And 2 of the orbitals, they go with a higher energy, they split up. Their family gets split up. This splitting is called as the octahedral splitting, or better we call as crystal octahedral field splitting. So they split up, and this is how it comes: dx square y square and dz square. Here we call this as delta 0.6, and this is delta 0.4 minus then the barycenter. Why? Because from that energy they fall as low as 0.4 and they rise up. So this should be plus, this minus. So dx square y square and dz square remains at the higher energy level, and this is called as the Eg level, while the lower energy is called as T2G levels. So here when they fall down with respect to that of the barycenter, this is what we call T2G, and when they rise up, it is called as the Eg levels. These are the levels. So this is the degenerate level, this is the excited level, and the excited level has a barycenter. With respect to the barycenter, if they rise upward, it is called as the Eg level, and if they fall downward, it is called the T2G level. In tetrahedral complexes, that is, with coordination number 4, the 4 negative ligands surrounding the metal ion lie in the direction between the 3 coordinate axes. The set of dxy, dyz, dzx orbitals will experience more repulsion from the fields of the ligand, raising the energy of these orbitals, while dx square y square and dz square, which have lobes in between the ligands, will experience minimum repulsion and will be lowered in energy. It results in the splitting of the d orbital. The magnitude of the energy difference of the splitting of the tetrahedral is much smaller than that of the octahedral field. I would ask the student to take a note of this that in tetrahedral field there is no center of symmetry, so that energy subscript G is not considered. dxy, dyz and dzx are called T2, and dx square, y square and dz square are called as E orbital. Instead of writing T2G or EG, you may write here T2 or E. The T2 level is raised up by 0.4 splitting of tetrahedral energy, whereas a level E is lowered by 0.6 magnitude of the splitting energy of the tetrahedral. There is a small workout here. You can see it is just the reverse of the octahedral splitting. In octahedral splitting, T2G was lower, while in the tetrahedral T2G, which occupies with the dxy, dyz and dzx, are raised up by 0.4 of the splitting of the tetrahedral energy, while the E level with dx square, y square and dz square is lowered by 0.6 of the splitting energy. With the red caption being written, the splitting of the tetrahedral is approximately equals to 4 by 9 of the splitting energy of the octahedral complexes. So student, remember here the factors influencing the magnitude of the crystal field splitting. So who are responsible? First, the nature of the ligands. The ligand with large negative charge and small size produce large crystal field splitting. You can see the spectrochemical series included: carbon monoxide, cyanide, nitride, ethane 1,2-diamine, ammonia, pyridine, ethylene diamine tetraacetate, iron, thiocyanide, isothiocyanide, water. You can go for the hydroxide, fluoride, sulfide, chloride, thiocyanide, bromide, iodide, etc. So the order you have to be very careful. You can see the first half, they are very strong ligand, while the lower part are very weak ligands. Number 2, the oxidation state of the metal. Crystal field splitting energy increases with the increase in the oxidation state of the central metal ion. I repeat, crystal field splitting energy increases. The splitting will be more with the increase in the oxidation state of the central metal ion. So the central metal ion getting more charge. If it is of +3, it will split more than that of +2 state. Size of the d orbital. For similar complexes of a metal, crystal field splitting energy increases with the increase in the size of the d orbital and the geometry of the complex. Crystal field splitting in case of the octahedral complex is nearly double the value of the tetrahedral complex. So we have already learned it before. Regarding the octahedral complex, there is a relation that you have to learn it, student. Electron will be preferred to go into lower energy, that is T2G orbital, than to occupy the higher energy EG orbital in the ground state to make it the most stable electronic configuration. So electrons love to be in the lower energy level. If they are in the lower energy level, they are more stabilized. The decrease in the energy due to the preferential occupation of the stable 2T G orbital is called the CFSE, where CFSE is equals to 0.6 splitting octahedral energy with number of electrons taking part in the EG level, subtracting out 0.4 the splitting of the octahedral energy of number of electrons taking part in the T2G level, where N indicates the number of electrons in the respective d orbital. And the distribution of the electrons in the octahedral complexes are being shown here. Student, I would ask you to take a short note of it. If necessary, you can take a printout of these very things, CFSE, crystal field stabilizing energy. When the number of electrons in the metal ion is 1, it will go to the T2G level as 1, and CFSE is -4. I have already told you before, this relation CFSE equals to 0.6 NEG minus 0.4 of the splitting energy of N2TG level. If you subtract it, you would be getting these values. So be careful. Then when you fill it up, it may come in your exam as well. Like calcium, it doesn't have any d orbital, so value of the CFSE is 0. For titanium, you can see here minus 0.8 of the splitting energy. So you can see it just goes down and then comes up and so on. For the tetrahedral complexes, the CFSE is something different. No tetrahedral complexes with low spin configuration has been formed. They are always with the high spin. This is due to the fact that crystal field splitting in the tetrahedral complexes are very small and is less than the pairing energy. So it can be always neglected. Now the number of d or electrons in the metal ion, if it rises from 1 to 10, and the number of the electrons there on the E orbital, we cannot call it as EG level, we just call it as E level. If it is here, the CFSE would be of this value. So tetrahedral complexes with less number of unpaired electron, low spin complexes, if delta naught is large strong field ligands like carbon monoxide, cyanide, etc., the electrons will try to remain in the lower T2G orbitals and get paired. In this case, the complex has less number of unpaired electrons and is called as low spin complex and vice versa. Explanation of the properties of the complexes according to CFT. First to go is about the magnetic behavior. Strong field ligands show very low spin due to, as it is more stable, and weak field ligands can cause high spin states to be more stable. You know that the number of unpaired electrons in the complex, we can predict the magnetic behavior whether it is paramagnetic or diamagnetic. Regarding the color of the complex ion, when light is absorbed by a substance, the energy of the photon raises the electron from a lower energy level to the high energy level. White light contains photons of all frequencies and colors in the visible spectrum. When white light is passed through a solution of the complex, the light gives a complementary color and reflects the rest. For in case of chromium with hexa water molecules, that means hexa aqua chromate 3 ion, the light absorbed when the electron is raised from one set of d orbital to the other and has a frequency of 5.22 into 10 to the power 14 hertz, which is of yellow color. So the solution of this ion appears violet blue. Before I go to the limitations of the crystal field theory, I would ask the student to see the board once more. So when you can see the electrons moving from the T2G level to the EG level, they absorb some energy. Without absorbing the energy, they cannot go to the higher level. In absorbing the energy, if I take such compounds like chromium with the water molecule, 6 molecules of water, So here the electrons would jump from the lower energy to the higher energy. In doing so, they absorb the energy. So when you are allowing the white light to pass through it, they absorb some energy. Which energy they absorb? It is found that they absorb energy which is equivalent to the yellow light. So if they have absorbing the energy from with the yellow light, they would be giving out the complementary color. What is the complementary color of yellow? It should be around violet, V-I-O-L-E-T, violet color. So if they absorb the yellow color, they would emit that violet color, so or the violet light. So better I can say violet is the complementary color of this hexa aqua chromate 3 ion. So this chromium 3 ion would be absorbing the yellow light and be emitting out the violet color. Limitations of the crystal field theory. It is considered metal ligand bound as purely electrostatic. But it cannot be. It should be also with the coordinate and covalent bond. It does not account for partial covalent character of the metal ligand bonds. Again, the order of the ligand is in spectrochemical series cannot be explained solely on the electrostatic ground. It failed to predict the relative strength of the different ligands. It kept silent about the possibility of double bonding between the metal ion and the ligand. And finally, it considered only D-orbitals of the metal ion and is silent about the contribution of the s orbital, px, py, pz and the ligand p bonds. That was about the limitations. Now regarding the stability of the coordination compound in solution, the first point to illustrate is about the kinetic stability of a complex. It refers to the speed with which the transformation takes place, which leads to the attainment of equilibrium. It refers to the speed, kinetic stability. Thermodynamic stability of a complex, that you have already learned, that students, regarding the dissociation constant. So if the smaller the value of the dissociation constant, greater will be the stability of the complex, because reciprocal of the dissociation constant is called the stability constant. So if you can make upside down, it is called the stability constant. In class 11 you have learned about dissociation constant. Here you would be learning about the stability constant, which is just an inverse of it. Number third point, for a given metal and ligand, the stability increases with the increase in the charge of the metal ion. Thus, complex compound having charge of +3 on the metal ion are more stable than compounds in the 2+ oxidation state. So if I give you Fe3 and Fe2, Fe3 will have more stability than Fe2+ ions. There is another more point to illustrate, that is Irving-Williams order. If you see, for the divalent ion of the first transition series, Mn2+ is the least and zinc the most. Regarding class A acceptors and class B acceptors, this should be B, it is misrepresented here. This is B, this is class A acceptors. Metal ions of group 1 and 2, the inner transition elements and early members of the transition groups from 3 to 6, from most stable coordination compound with ligands containing FON, F-O-N, that is fluorine, oxygen and nitrogen donor atoms. And for class B acceptor, metal ions like rhodium, palladium, silver, iridium, gold and mercury having filled or nearly filled the orbital form stable complexes with ligands containing heavy members of fluorine, oxygen and nitrogen donor atoms. Regarding the macrocyclic effect, a cyclic multidentate further increases the stability provided there are no unfavorable steric effects. And finally, to go with the chelating effect, complexes formed by chelating ligands are more stable than their monodentate analogues due to the reduced strain in the chelate. Like CuEn2 plus is more stable than CuNH3 2 plus. So student, those who are having chelates will be more stable than those with the monodentate. I would ask the student to see the board once more. Students, within these two compounds, you have to tell me which is more stable, which is less stable. Here, copper, it joins the hand with En forming a chelate. You can see they are forming a chelate. They are forming a chelate. How? As they are forming a ring. So forming a ring is called as a chelate. But in case of copper here, they are added with ammonia, which is a monodentate ligand. Being a monodentate ligand, they are less stable. While they form a chelate, they form a ring, they are more stable. So more stable, less stable. This is the last topic for the coordination compound. We will go with the importance of the coordination compound. Some few importance I have illustrated, particularly EDTA, ethylene diamine tetraacetate. They are used to estimate the hardness of water. The iron in hemoglobin and magnesium in chlorophyll are stable due to the forming of complexes. Silver and gold metals are electroplated from their complex salts like KAgCN2 and KAgCN2 respectively. I made a wrong. It is just corrected now that Ag and Au, silver and gold metals, are electroplated from their complex salt formed by KAgCN2 and KuCN2 respectively. Cis platinum with ammonia and chlorine, we call this as diamine dichloridoplatinate 2. This commonly called as cisplatin is used as an anti-tumor agent in the treatment of cancer, while vitamin B12 cyanocobalamin is a complex used to prevent anemia. So student, this is all about the different importance of the coordination compound, and I felt really very interesting to illustrate it vividly. Though the time is running out, I will have to say you goodbye and good night.